Hey everybody. Today we're talking about covariance and correlation. Both of these quantify the direction and strength of the relationship between two random variables. So covariance, to start with, is defined in a similar way to variance using expected value. A bit more specifically, it's the expected value of the quantity x minus the expected value of x times y minus the expected value of y. And we have two different notations. We can write COV, parenthesis x comma y, or sigma sub xy. In terms of interpretation, when covariance is positive, x and y both tend to get greater or smaller together. And when covariance is negative, the opposite is true. So when x gets bigger, y tends to get smaller and vice versa. One important warning is that right now I'm talking about the covariance of random variables, and in a little bit I'll talk about the correlation between random variables. And that's related to, but not the same, as when we talk about covariance and correlation of paired data. Now, covariance is typically computed using a different formula, not just doing the expected value of x minus mu sub x times y minus mu sub y. We typically compute it using the formula the expected value of x times y minus the expected value of x times the expected value of y. And that's a very reminiscent formula to the one used to compute variance in the single variable case. And the proof is exactly identical. You FOIL out the thing in the inside the expected value in the middle of that line. You break it up using the linearity of expectation, things simplify, and you get the formula on the right. Let's do an example. I think that's when things start to get a little bit more clear. Here we have a table showing a simple joint distribution of two discrete random variables, x and y. I want to compute the covariance between those two. I'm going to use the formula from the last slide. This is a great place to pause the video, try the computation on your own before looking to see how I do it. So the first thing I need to do is to compute the expected value of x times y. And I did this by making a table just of all the values of x times y for the different combinations of x and y. So for instance, when x is 2 and y is 3, xy is 6. Now I need to do the summation across all the possible values of x and y, doing the summation of x times y times f of x comma y, the joint probability mass function. So there's a lot of arithmetic there. There's about 10 things I have to multiply and add up. When I do all that arithmetic, I get 5.09. To compute the expected value of x and the expected value of y, we just find the marginal probability distributions of x and y. And I've literally written those in the margins of the table, as you can see here. So now I have two single variable distributions with probability mass functions f sub x of x and f sub y of y. I compute those expected values in the usual way. I get the expected value of x is 2.30. The expected value of y is 2.39. Now we're ready to just plug into that formula to compute the covariance between x and y. We do the expected value of xy, 5.09, minus the expected value of x times the expected value of y, 2.30 times 2.39. We do out the arithmetic. We get negative 0.41. And the fact that this is negative indicates that as x increases, y tends to decrease, which I think is pretty intuitive when you look at the distribution that I wrote there. You can physically see that as x gets bigger, y tends to get smaller. Now, covariance depends on the scale of the variables involved, so it's hard to interpret. And in this way, it's very similar to single variable variance. Natural thing to do is to address that by dividing the covariance by the individual standard deviations, sigma sub x and sigma sub y. And when you do that, the result is a unitless measure that's always between -1 and 1. So what we have, the formula that we have written here is for the coefficient of correlation between two random variables, x and y. It's the covariance of x and y divided by sigma x, sigma y, divided by the individual standard deviations. Going back to that same example that we were looking at a minute ago, let's compute the correlation between these two variables. We already have the covariance, so all we need are the individual variances, the individual standard deviations. And we do that just by direct computation using the marginal probability mass functions. We do the expected value of x squared to get 6.46. We do the variance of x by doing the expected value of x squared minus the expected value of x quantity squared. We get 1.17. Similarly, the variance of y is computed to be 0.56. Overall, we get the individual standard deviations 1.08 and 0.75. So, putting that all together, we get the coefficient of correlation, negative 0.41 divided by 1.08 times 0.75, we get negative 0.50. Now, correlation always runs between negative 1 and 1, and when we have a negative covariance, we also have a negative correlation. So, between 0 and negative 1 in this case, we'll consider that to be a moderate negative correlation.